And then these are the sea surface height verifications for May 5th, and June 16th, and I guess that's one day off, June 15th. So anyway, that was our first successful demonstration of the loop current eddy shedding event 2 months out. Okay, so I've been showing you sea surface height, but now I'm going to show you a series of surface speed plots, okay? And when I first started this, I like to show sea surface height. It's because we observe sea surface height with altimeters, or I'd show sea surface temperature. It's not very useful in the summer, but it's good in the winter, and we have lots of sea surface temperatures. Well, the oil industry is really not interested in those. They're interested in velocity because that's what impacts their rigs, okay? And what I'm showing you here is a series of analyses and forecasts every week, starting in June 2nd, 9th, 16th, 23rd, 30th, 7th, July 14th, July 21. And when I say best analysis, that's after we've assimilated all the available observations. That's what we think the true state of the ocean really looks like. And then this is the 2-month forecast. So we go back 2 months, we do the forecast. So this June 2nd should, if this forecast is any good, oh, sorry again. If this forecast is any good, it should look like that analysis, okay? And again, it depends on how many observations you have, how good your initial state is, all of these things. But this is kind of the acid test. So how does this one look to that one? Well, to order one, it looks pretty good, okay? And this was right, when it was starting to separate. And here's where it did separate, and here's where it stayed separated. So here's the forecast, here's the analysis. And these are just kind of the, the sanity checks that we would go through and look at. This one, I know you're going to see little differences, but order one, they're quite similar. I'm going to show you that this isn't always the case. And in fact, in 2014, this year, it's been a really hard year for predicting the loop current eddy shedding because, well, I'll get to it, but if you're familiar, if you know if the Gulf of Mexico looks like this, the last few months, it's been very energetic in the northern Gulf, and we've had a detachment, a reattachment, a detachment, a reattachment. I think we're on the cusp of another detachment. It's been a difficult prediction period. Okay, so I showed you speed just now, and I showed you height at the beginning, but of course we can plot anything, and a lot of times we do. So I'm trying to convince you that a loop current eddy has shed by showing you the 17 centimeter of the height contour. Well, if you look at the 10 centimeter contour, it will definitely be shed. Or if I look at the 20 centimeter contour, so it's very subjective. So a lot of times we look at something like the temperature at the 22 degrees C isotherm at 100 meters, or we can look at the salinity, the 36.2 isohaline at 200 meters. Any prognostic variable you can extract, you can do the ensemble statistics on, and in each of these cases I'm just showing you the analysis and the corresponding 2-month forecast, and again the height, temperature, salinity, and speed. But the oil industry, they always want to just look at the speed. We've also done some validation with depth, okay, to look at the accuracy of the profiles. And I have 2 cases here. These are temperature profiles. The top case is for a 3-day forecast. I'll explain what the curves are in just a second. The middle are the 10-day forecasts, and the bottom are the 17-day forecasts. And this case on the left is for an observation out here. I'm going to try to get this right. Out here in the Western Gulf. In this case, on the right is for an observation out here in the Eastern Gulf where it's much more energetic. And what we're looking at on the left is the actual temperature profiles. Okay, so the red is the mean, and all the black curves are the individual. There are 32 individual profiles for each member. In the middle, we're looking at the error or the forecast minus the observation. And then on the right, we're looking at both the bias and the RMS error. The RMS error is shown in red and the bias in black. And really, what I want to show is that in the Western Gulf, where it's quite low energy or quite quiescent, we do pretty darn well on the biases and on the errors. So if we look at the error here is 0, and it's close to 0 out in the Western Gulf for both 3, 10, and 17 day. You expect the errors to get a little bit bigger the longer the forecast is, but in this case, out in the Western Gulf, they don't do that so much. In the eastern Gulf, where we have this loop current trying to shed at this point in time, we don't do that well, and you can see that the errors are pretty large. They're out to about 2 degrees C here, and they're just off the chart almost in all these cases. So, I think we have some work to do in terms of improving the subsurface forecasts when we get out into the longer horizons, but there it is. And, we have to look at the subsurface as well as the surface. Okay, so now I just want to focus on, as I think I mentioned, we did a 5-year reanalysis. We went back to 2010, ran 60-day forecasts once a week from 2010 into the future, or into the present. And then we just went back and identified all of the major loop current eddy shedding events that have occurred since then. So we start with Franklin. That was that shed, or this is the analysis on April 11th. We went through, and week by week by week, we determined, okay, this particular eddy shed on this week. You really can't pinpoint it to a day, but to the week anyway. We looked at the independent altimetry. We looked at other independent data sources, when and where they were available. And so we said, okay, Franklin shed on about June 6th. So here's where it started from 2 months earlier. Here was the forecast, and here is the analysis. So that forecast should look like that analysis, if it was a good forecast. Okay, we didn't quite get this, but it's a little bit subjective because of the particular 17 centimeter contour line. But, it's qualitatively okay, I would say. I mean, the core of the loop current eddy, which is what the oil industry is really interested in, is at about the same location, and that was important in terms of its impact on the deep water rigs. Here's what they call, I think Horizon Marine names these eddies. I've never quite figured out who gives them these names, but everybody in the industry seems to agree that they give them these names. So here's Galileo. The analysis indicates that based on this metric, the 17 centimeter contour, it shed on May 1 of 2011. We didn't do so good for this one. I mean, I would argue that the 2-month forecast wasn't so good for this particular event. Eddy Hadal, which is shed on July 31st. The analysis and the forecast are really pretty good, pretty similar. So here's a case where we did quite well. Here's a case where we didn't do so well. I think part of the reason we didn't do so well here was there wasn't enough spread or uncertainty amongst the various ensemble members. You see basically one primary mode, and that's this mode right here. That's the same mode here. Down here where we did quite well, you can see that the ensemble spread or the forecast uncertainty is much greater. Don't get confused when I say forecast uncertainty. It's more the ensemble spread. We're covering more of the possible dynamical modes in the Gulf of Mexico here. So not enough spread amongst the various ensemble members. Good enough or sufficient spread gives you a better forecast. Just continuing on, this is Eddy Icarus. It was observed to separate in early November of 2011. Here's the analysis. Here's the forecast. The shape isn't quite right, but again, the core of the eddy is in about the right place. So the customer, the oil industry in this case, is fairly satisfied with this particular prediction because it tells them where the strongest currents associated with the loop current are that are going to impact their operations. Eddy Jumbo, June 17th of 2012. We certainly didn't do so great with the neck, and the size was a bit off. Again, maybe not enough ensemble spread amongst the members. And then here's Eddy Kraken, which was in March of last year, 2013, and we did pretty good there. So these are the major eddy shedding events of the last 5 years, and these are the 2-month predictions associated with them. Am I doing on time? Okay. So how well are we actually doing? And so now I'm going to show you a series of metrics that we use to validate or assess the quality of the forecast. And how we're doing that in this plot is we're calculating anomaly correlations. And this one is with respect to the sea surface height. So how we calculate an anomaly correlation is we will run the model for a year just in hindcat, just doing a nowcast or an analysis every day. So we have a year's worth of what we call true model states. And then we have the 60-day forecast. So we will compare the 60-day forecast to the analysis, we'll calculate an anomaly correlation between those two fields, and we'll plot it. And then in this case, we've averaged it for all the grid points over the entire Gulf of Mexico. And so what you're looking at is the anomaly correlation that goes from 0 to 1, and you're looking at the forecast length, and just from a weird plotting thing, it goes out to 56 instead of 60 days. But we consider an anomaly correlation of 0.6 or greater to be demonstrative of forecast skill. Okay, so that's why I've drawn this blue line here. The black line is the model anomaly correlation itself. The red line is what we call persistence. That's basically a forecast of no change. So if you don't allow the forecast to dynamically evolve in time, you get less skill, of course. But so for the SSH, and then I've plotted 3 different years here, 2010, 2011, and 2013. We're showing skill with regard to the sea surface height well beyond 56 days, or just at least out to 56 days. There's some interannual variability in how well you can forecast based on this metric. So it's a bit less for 2011, and it's even less for 2013. That can be for a variety of reasons. The loop current may be more energetic. That there's more shedding events in 2013 than there was in 2010. There's only one in 2010. But it gives you an idea. With respect to height, we can do quite well if you use this metric. Okay, now I'm going to look at the surface. I'm going to look at the speed correlations, the speed anomaly correlations. And so this is for the surface, and then now you can also look at this at depth. Okay, and so we're looking at it at depth. We're looking at it for different years. This is the speed at the point at which it crosses the 0.6 correlation value is where I say it loses useful skill. So we're showing skill with the surface speeds in 2010 out to about 28 days or 4 weeks. 2011, it's a little bit less, and 2013, but these aren't terribly different. And why did I look at depth? Well, I was interested to see if there was, a strong depth dependence in terms of the predictability, and not really. These are fairly barotropic in terms of their predictability. It's all around 28 days right here, there's a little bit, but there's some interannual variability between the predictability. That's kind of a mouthful, but. This is the temperature anomaly correlations, and these are really, really high, and that's because we have a lot of SST observations. We have tons of satellite surface temperature observations. So you have great skill. It just doesn't change that much, to be honest with you. You have less skill at depth. That's to be expected. But they're fairly predictable. They're predictable out to 5 weeks on average. So that's not too bad. And then finally, the salinity. Okay, well, we're not doing very well with salinity, but that's because there aren't very many salinity observations. So the fewer observations, the harder the predictability, and that's reflected in these maps. So we only have skill out to about a week in 2010 for the surface salinity. Now, interestingly, if you look at depth, there's a subsurface salinity maximum in the Gulf of Mexico, right? And that's why, and that's, I guess it's like a mode water, right? I don't know if it's technically a mode water, but there's this fairly persistent subsurface salinity maximum, and so that doesn't change very much from as to forecast length or from year to year. So you get pretty good predictability of the subsurface salinity, much better than you do at the surface. Of course, those were averaged over the entire Gulf of Mexico, but they're actually you do the anomaly correlation at every grid point. And that's what I'm showing here. And this is just for the speed. So this is the 1 week anomaly correlation spatially plotted. This is 3 weeks, this is 5 weeks, and this is 8 weeks again for 2010, 2011, and 2012. Red, they're highly correlated, or there's a high correlation, and blue, there's a low correlation. Of course, you lose predictability the further out in time, so you have much more predictability, especially in this region, after 1 week, and much less so after 8 weeks. And that's to be expected. The forecast is going to drift away from the analysis. Okay, so we've generated all of this output. What I say, it was 130 gigabytes per 32 members per 60-day cycle, something like that. And the challenge then is to turn it into something useful, so that an operator on a rig or a guy on a ship, they need something that they can look at and say, okay, what am I looking at here? What have you generated? What can you do for me, right? And so from the ensembles, we can generate probability distribution functions. You have a population at each grid point, a population of 32, and so you can generate a PDF. And based on those PDFs, then you can just say, okay, well, what is the probability of something with some kind of threshold? And what I've extracted here is the probability of the surface currents being greater than 2 knots, or about a meter per second, okay? And I've just done this for an 8-week cycle. So this is September 21st of this year, and this is the 1-week forecast, the 2-week forecast, and so on. So this is the 8-week forecast. And where it's red, there's a high probability of seeing a current that's greater than 2 knots. Okay, and it's where you would expect it to be in the area of the loop current, the edge of the loop current, where the velocities are fastest. And then it starts to drop off. The probability drops off, but it's not that the currents. Remember, this is a probability plot. This is not a plot of the velocity itself. This is a plot of the probability of seeing a velocity of a certain magnitude. And what happens is that your PDF is basically getting flatter. I mean, a probability distribution function would have a dominant mode, in this case at 2 meters per second. Well, that probability distribution function is simply getting flatter as the forecast length gets longer, and so you're still likely to see a strong current out here, but it's just that the probability is less because the PDF is flattened out. So anyway, this gives the guy on the ship or the guy on the rig, man, if I'm going to be operating in this area, it's pretty likely that I'm going to see strong currents. Okay, well, we can take that a step further, and we can integrate the PDF into a CDF, a cumulative distribution function. And so this is now what we're trying to do is these risk management tools, or these risk management matrices. And so this is a risk management code or a risk assessment code, and it plots the probability of an event against the impact or the severity or the threshold of that event. Okay, so one of those, I'm doing this on purpose this time. One of these is one of these blocks here, okay? It would be one of these blocks. So this is greater than 75%. This is between 50 and 75%. This is between 25 and 50 and less than 25. I choose those. I have a CDF in front of me, a cumulative distribution function. I can pull off any percent along that CDF that I want. And then I choose these two. And what I've chosen to look at in this case is the surface velocity or the surface speed. And I've chosen the threshold so that level 1 or very high impact is greater than 1 knot or 0.7 meters per second. Level 2 is between 0.5 and 0.7. Level 3 is between 0.25 and 0.5. And level 4 is less than 0.15 meters per second. Those were the thresholds that my customer was interested for in their application for the oil rigs. And I said, okay, well, what currents can't you operate in? Okay, so if you see a red here, there's a very high probability of a current that will cause you trouble. This is for the rigs, but it could be for a glider that can't operate in strong currents. It could be for small boat operations where the sea state's too high. It can be for, you can choose what you want this to be. So this is for the velocities, okay? But we can also do it for, say, the winds. So if the winds are, say, greater than 30 meters per second, then that's going to have a big impact on your at-sea operations. If it's between 20 and 30, that's going to be a level 2, a high. Between 10 and 20 would be medium, and say less than 10 would be minimal. So high probability of a 30 meter per second wind, stay away, drive the other way. Low probability of a weak wind, don't even worry about it. Go out there and do whatever you need to do. Remember, these are probabilities, though. They're not absolutes. You always have to put that caveat there. And then this is the same for the waves, okay? So this is for the sea state, and this again would be small boat ops or something like that. And here, these are the thresholds for the sea state. So high, greater than 3, very high, greater than 3, high, between 2 and 3, medium, between 1 and 2, and minimal, between 1. So it's time dependent. It changes every however often I save the output, it changes. It's a time dependent quantity. It's spatially variant, obviously, but it gives you an idea. It gives you a capability to compress all of the statistical information into something that is very easy for somebody on a ship or somebody on a rig having to make a quick decision to do that. Oh, and yeah, this is just the last one. So the ones before were individual for velocity, waves, and winds, but now we can actually calculate the joint probability of occurrence. So we take into account all 4 of them, and so now the impact or the severity here takes into account all of the quantities. And in this case, it's dominated by the surface speeds, by the surface velocities, but it's slightly different, and it's a joint probability in this case. So we put everything on the web. Right now it's password protected, but I don't think I've ever said no to anybody who's ever asked me for the password. So if you want to take a look, let me know. But this is just the front page of it. It puts the latest forecast out there. This is an older plot, but at the time this was what we had out there. We generate all these different products, or all these different quantities, I guess you could say. These are animations. These are snapshots. The mean speed, the variance of the speed at depth, the height, the temperature, the salinity, and so on. And then once you bore down even further into it, so this again was a screen snapshot when it was running in 2013. But this would be the analysis, and this would be for the speed standard deviation, for example, that would be the 1 week forecast, on and on and on. That would be the 8 week forecast. So you can go in there, click on anyone, pull up whatever map you might want. Okay, so I gave this brief. This was a closeout brief that I gave last May in Houston. And at the time, I pulled off the latest analysis and forecasts. And 2014 has certainly been a challenging year, as I mentioned earlier. And I said, well, is a shedding event imminent? Okay, I think it is. Here is the mean speed these are the analyses. This is for the speed, the height. This is the uncertainty or the spread. And this is the 18 degrees C at 200 meter. I included that because a lot of people use that as a proxy for when a shedding event actually occurs. And then these are the corresponding 2-month forecasts, or the forecast for June 22. So the height went from this state forecasted into that state. Okay, low variance at the analysis time.